we'll kick off with a very quick overview what those two projects are actually about. And once we're done with that, you have a short moment to ask some questions because we want to make sure that everybody is involved in this session proactively. And then we'll really dive into the details. What are the challenges for the automotive industry? How can all the research institutions in Europe help to solve these challenges? And how do all the stakeholders need to collaborate in order to move forward together? So we'll conclude by the end around 11:30 with a panel discussion that you're also very welcome to join with your questions. So make sure to fill that chat with live and with your questions. If you want to join us already to kick it off, maybe use the chat now to just type in your name, what brings you here, what organization do you work for, what do you want to learn in this session, or what challenge do you want to solve? So let's use the chat while we're presenting also to connect and to exchange information. That's what the session is for. I'll just kick it off. Welcome, everybody. Please join me in the chat. Let me know who you are. So in order to catch up for some of the time we lost in the beginning, we'll have a look into what revolution actually is about. And who better to tell us than the project coordinator for Revolution, Emre Elmas. In his main job, he's fundraising project responsible at Farplus, one of the top 250 industrial companies in Turkey, and a very important solution partner for the automotive industry. So very much at the heart of what this whole project is about. Welcome, Emre. Great to have you with us.
Thank you very much, Zach. Actually, it was really a good introduction to the session, and also it was really good welcome, a calm welcome for the people who participated and joined the session. Thank you very much for it.
I'd say the screen is yours, Emre. If you want, you can already start sharing your presentation, and then we'll give you the full 10 minutes to give us an insight into Revolution.
Okay, thank you very much. I'm sharing my screen now. There is a problem in here. Okay. Now you should be able to see my screen. Yes. Is everything okay with my screen?
Yes. Yes.
Okay, that's great. Thank you very much. And actually, as Zach indicated, I'm Emre Elmas, and I'm the coordinator of the Revolution project, and I will give a short introduction of Revolution and what we are targeting through the Revolution activities. Actually, the Revolution project has been funded by the European Commission and started by the beginning of the 2021. And the title of the revolution actually summarizes the targets and of the objectives of the revolution, and the title is that supporting the electric vehicle revolution through maximizing electric vehicle range and end-of-life vehicle recovery through optimization of recycled plastics and advanced light materials. Actually, to do all these objectives, actually, and sensors will be crucial for us. And actually, Revolution is bringing a new technology and also new innovation into the industry by using machine learnings and artificial intelligence technologies. Actually, the main target is to optimize and also the input of recycled materials into the injection molding processes for delivering and producing high quality parts. And in that part, actually, the machine learning and also the artificial intelligence will be used by collecting data from the plants and also injection molding machines. After collecting all these data, we will analyze them and we will compile all these ones also to deliver high quality components. And actually, there are two main sub-objectives of the revolution. One of them is reducing the weights of the components comparing to the alternatives, and demonstrating that actually producing the components that will be recycled in their further usage and also further lives. So we have 4 use cases for that. One of them is backseat panel, the other one B-pillar cover, the next one crash box, and the last one is the lower rear bumper. Actually, since I will give a further details of all these ones for now, I want to show you a general picture of the actual automotive system. What is the actual automotive system? As you can actually in this graph, you can see that how we are producing how we are generating the components, raw materials actually from mines, and how we are using them into the flow of producing of the vehicles. So after we generated the raw materials from mines and bringing them to the industrial process, and in there we are using them to produce the components, and then you can see we are combining all of them to get a final product, which is a vehicle. And after that, some of these components on the vehicle can be recycled, and then some of them are the weights. So while some of these components are returning back to the industrial process, production process, some of them going to the waste. And in how Revolution is providing the contributions of all these flow and the supply chain, you can see we are calling this one as the industrial revolution. And in the plants in where that we are producing the components for the electric vehicles, actually Revolution bringing new technologies that I mentioned, as the machine learning, artificial intelligence, and also other advanced materials that we are developing and handling. And after that, so actually we are making the revolutions, making the smarter industrial processes. And after that, we are bringing new technologies into the recycling process, as making the components more recyclable. And by the end of life strategies, and also making the recyclable components and the materials, we are aiming to increase the amount of components and the materials, as maybe the waste that can be returned to the industrial production processes. So Revolution also, while facing with the high challenges of the automotive industry and bringing new solutions to them, the environmental impacts from the automotive industry also is decreased. You can see now the all partners of the revolution. We have Tier 1 companies, we have OEMs, we have research institutions, we have material developer companies, universities, sensor technology, sensor developer institutions, and also machine learning and AI developer companies. So we are covering the almost all supply chain of the automotive industry, and all together we are collaborating to make the world and the future is better. So actually, I want to mention about the general overview. Actually, I provided already them, but also I want to mention that the AI platform will use the data from 3 areas of the production process to predict the part quality when using recycled materials. In there, actually, the sensors also will be important for us, that we will embed in the injection molding machines. And after that, the project, the platform that has been developed by the project and the range of recycled formulations, including self-reinforced materials, will provide us to produce actually innovative components that offer lightweighting, superior performance, and end-of-life advantages for the future of their life. And actually, our target for the lightweighting is that between 10% to 40% comparing to the current alternatives, that the demonstration components. And the other objective of the revolution, producing the components with the rate of 80% as recyclable and reusable. So actually these are really important for the automotive industry. And this is the first use case that we are handling provided by the CRF, which is backseat panel. Actually, the component is currently made of a formed steel sheet in the current environment, and our target with the revolution is making these components, converting these components to an SRPO materials with the lightweighting target of 55%. And this is the B-pillar cover. Actually, this is a 2K dual part and will be transformed into a monomaterial injection molding component by using post-industrial recycled PMMA. And the use case has been provided by the Mayer. And the next use case is the crash box. Actually, this is the interesting part for the component also. For the sensor integration, currently this component commercially produced by using the steel, and in the Revolution project, our target is transforming this component as a fully polymer solution. And by embedding the sensors that which will be developed, which are being actually developed by the Revolution to monitor the well-being and also health conditions of the components while it will be used on the vehicle level in the real life environment. So actually my colleagues from the IMEC will give further information about them, I think. And the last use case is the lower rear bumper. Actually, it is a colored aesthetical part, so it makes it so difficult to produce this component with the fully recycled materials, since there are high expectations and also requirements from the automotive OEMs. And also it is really difficult to attain the appropriate color and the gloss using post-consumer recycled materials. But our target is to optimize the use of PCR polypropylene by the achieving 20% weight reduction, but also keeping mechanical and the physical properties of the components, which is so important for the Tofaş actually. The last two components, the crash box and the lower rear bumper, are provided by the Tofaş and together with the Far Plus. Thank you very much for your all times and for your attention. If you have any question and further comments, please let me know.
Thanks a lot, Emre, for this speedy write and overview of what Revolution as a project is about. We already saw a lot of various stakeholders involved into the project. And it's also a tasking undertaking. Those are not just some superficial decorative elements of the car, but really some also safety critical elements. So it really is a very interesting field. Emre, please also join us in the chat, maybe also with your contact details if people want to connect with you on LinkedIn. And in the meantime, we'll move on to have a look into what LEVIS is about, because to me, as an outsider, both projects somehow are active in the same area, but there are significant differences and various approaches. And what those are, we now hear from José Ramón Valdés. He, on the one hand, is looking into collaborative R&I and is the programs coordinator at Itainova. So basically the Aragon Institute of Technology, which really is the enabler for collaboration and research in the region in Spain. And he also is the LEVIS project coordinator. Jose, welcome. I see you have your slides ready, so the screen is yours.
Thank you very much. I hope the sound is you can hear me well. So I will give a brief introduction to the LEVIS project. Well, you have already explained the title is Advanced Light Materials for Sustainable Electric Vehicles by Integration of Eco-Design and Circular Economy Strategies. It is, as Revolution, an H2020 project addressing the same call, which is advanced light materials and their production processes for automotive applications. It runs for 3 years. It will end in January of next year. It has a contribution of 5 million euros from the European Commission And the Itainova, the Aragon Institute of Technology, is the coordinator of this project. The consortium is formed by 13 partners, 8 of which are RTOs and 5 are industrial companies from 7 countries in Europe. 5 of them are RTOs working in materials and technologies, in different materials and technologies. We have also industrial partners providing demonstrators from different parts of the car, and we also have companies working in horizontal aspects such as integration, replication, exploitation, dissemination, or circular economy. The main objective of LEVIS is the development, verification, and demonstration of lightweight components in electric vehicles. We will work, or we will address 3 industrial demonstrators. One is a suspension control arm provided by Marelli. Another one is a battery holding set provided mainly by Yesilova, although there will be also Mersen will also work on this demonstrator. And we have also a cross-car beam provided by Tofaş. This general objective will be divided or deployed into different specific objectives, which are the demonstration of the feasibility of lightweighting, developing sensor technologies for service life monitoring, also developing cost-effective manufacturing processes, advanced simulation workflows to support all of this and to address structural integrity and prediction of the service life. We will also work on suitable end-of-life approaches for the materials and the components that we will develop, demonstrating the possible replication or potential replication to other components of the electric vehicle, and meanwhile maximizing the implementation of these technologies and materials. We are looking at reducing the weight of the vehicle, also reducing. We are also looking at reducing the production costs, increasing the recycling rates, reducing the global warming potential, and replicating these technologies in other components of the electric vehicle. All these objectives will be based on a number of technologies that we will work on in the project, and these are multi-material structural components, cost-effective manufacturing technologies, techniques to improve the joints and interfaces between these materials, simulation methods for life predictions, also the integration of sensing and health monitoring capabilities, strategies for end-of-life harvesting and reuse of the composite parts, disassembly techniques for the metal composite joints, and the application of eco-design principles and LCA tools. We will have the project will have different work packages. Demonstrator development will run throughout the project, and in parallel we will be working on the development of these technologies and the application to the demonstrators and the final validation. So far, the main results that we have achieved in LEVIS, although of course we will have to wait to the end of the project to have the final prototypes and the validation, is regarding the design. We have developed, or we have come up with the novel designs of these demonstrators, introducing hybrid metal designs that are easy to disassemble and already achieving interesting weight reductions at the component level, which we expect to have an impact on the overall structural weight of the vehicle. Regarding the materials, we have also developed cost-effective bio-based carbon fibers with good mechanical properties, TP thermoplastic tapes, including either standard or bio-based carbon fibers. We have also developed and used short fiber composites made of recycled carbon fibers, and we are working on the recovery of the composite constituents. Regarding the hybrid design, we have also worked on side beams made of aluminum with reinforced with carbon fiber reinforced polymer patches. Also, the laser texturing of aluminum to improve the bonding with carbon fibers, and the finally development of innovative thermoplastic acrylic matrix for these components. Regarding sensoring and sustainability, we are working on the manufacturing and integration of sensors, the development and integration of a structural health monitoring system. We have also developed debondable on-demand structural adhesives with very high debonding effectiveness, and an eco-design toolkit to integrate this life cycle and circular economy into the design process. By working on all of these technologies and addressing the objectives already mentioned, we are looking to, in the mid to long term, to significantly contribute to the weight reduction of the components and the vehicle, the speed up of the production and reduction of the time to market of these components, the identification of safety and performance issues by using these sensor and structural health monitoring technologies, and finally developing and implementing end-of-life strategies that will allow us to reuse or recycle most of the materials. This is the introduction to our project, and if you have any question or comment, I'm looking forward to hear it. Thank you very much.
Thanks a lot, Jose. Actually, you made up some time for me, so I'm personally very grateful for your speedy presentation. Let's keep you on screen, and we'll take the full 5 minutes to have some questions. Also, if our participants, the audience, has questions, please let me know. Just type them in the chat. This is your chance to get more information about the two projects. Emre, if you also want to join me back on screen together with Jose, we can just dive a little bit into it. Now, I'll just ask the dummy questions here, because maybe some in the audience are in a similar position as me. Both projects sort of operate in the same area, but with a different approach. For me, as like the dummy from the outside, it sounded like, Emre, you come in more like with a tech approach and with a data and AI approach. And LEVIS, Jose, also covers really the questions of the material and use and some material research. Is that a fair summary of the differences?
Well, yeah, LEVIS addresses mainly weight reduction by using composite materials, by developing and introducing composite materials in the components of electric vehicles. Of course, we are also looking at, as mentioned, multi-material, or the possibility of using multi-material technologies, like combining metals and composites. But the main focus of the project is composite materials and the technologies that revolve around them, as mentioned, sensoring, structural health monitoring, joints, also simulation technologies, LCA, eco-design, etc. But yeah, the main focus is that composite materials, development of new bio-based and lighter materials, and other technologies.
Thank you. And Emre, was that a fair summary of Revolution?
Actually, I can say that actually Jose made a good summary of the LEVIS. And in terms of the Revolution, yeah, you are right that we are using the machine learning. Actually, we are putting the machine learning and AI also in the center of the Revolution. But around that, by using these ones, we are targeting the lightweighting of the components, and as well as using the recycled materials. That is the main differentiation of both project, maybe. And please correct me, Jose, and if I am right, the LEVIS project is targeting the structural components of the vehicle. But on the Revolution side, our components are not fully structural components. What I mean by the structural components is that there are some components which are more, how can I say, puts the structure of the vehicle Some of them gives the aesthetic, some of them increase the safety, etc., etc. So in here, the revolution components are not fully structural components. So that is the another differentiation, and we are using the recycled materials for lightweighting. Actually, that is the another challenge of the revolution.
Thank you. That made it much clearer for me. Now you bring together a lot of stakeholders, and I think one of the big challenges probably is that it's not only about researching a new material or a new approach, but now you really have to think the whole life cycle until also end of life and then recycling at the very end. So what extra challenges did that bring into running or coordinating the project, operating on such a long timeline? Maybe Jose, if you want to answer, because I think we lost Emre for a bit.
Well, yes, of course. Trying to integrate to work on all these technologies and applying them to these to the components brings several challenges, and of course sometimes there are risks that appear, and maybe you have to apply some mitigation actions to correct this or to save these risks. But yes, I mean we are working from the design of the components and all the way to the recycling and reuse of the material. So yeah.
It's a long timeline to look into. I'll speed
really
up things here, Jose, because I just saw that there's 2 questions in the chat, and we'll very quickly cover them because it's awesome that we have questions in the chat. Bernd Nass wants to know, are there also flammability requirements in scope, for example, for battery materials and boxes? Who wants to answer very quickly?
Well, we are not, as far as I remember, we are not looking into those in the project. We are more looking into the structural requirements.
Okay.
And in Revolution, we don't also.
And then Jan wants to know, at Jose, is the debondable on-demand adhesive a commercial product developed in the LEVIS consortium?
Not yet. We are. It is still at research research and development level. It's a technology that we have been working on at ITA for several years, and it's giving promising results, but it is not yet commercially available.
Okay.
All right. Thank you.
Those are good questions, though. Jose and Emre, please also have a look into the chat, and maybe you can provide more information to Jan or even to Bernd in the chat. Use the chat to have the discussion as parallel to what's happening on screen. Then we make the best use of this tool here. So thanks a lot to the both of you for really keeping it tight and crisp. And now we'll actually talk to some of the stakeholders involved in the project and get more information. Thanks a lot, Jose. Thanks a lot, Emre.
Thank you very much, Zach. Thank you very much for your moderation.
So for the next 20 minutes, we'll dive specifically into the perspective from the OEM stakeholders. And in that regard, starting again with Revolution, will be Kemal Ekbij. He's running the R&D Center and incentive responsible at Tofaş. And we heard already Tofaş is very deeply involved into the project. One of the big Turkish automotive OEMs producing and working with Stellantis Europe together around since roughly the 70s, and running their own research and development. So not just executing, but really deeply involved into the research, such, of course, also integrated in through the project. Please let us know what challenges are OEMs facing and why are they relevant in this context. Welcome, the screen is yours.
Thank you very much, Zach, for great moderation and introduction. Let me share my presentation.
It takes a moment. I think you just started sharing, Kemal, right?
Yes. Can you hear my voice?
I can hear you, but we cannot see the presentation yet.
Okay. Right now I'm going to have the presentation, the overview of what is the challenges in automotive industry? Not
Perfect.
only
Now we can see it.
project,
Yes.
but general perspective I am going to be presenting. Can you see it right now?
Yes. We can see it and you're ready to go.
I cannot. Yes, also I can see it right now.
We can see your presentation,
Okay.
Kemal. So if you want, you can start.
Okay. I would like to share you information about the challenges advanced technologies for automobile sector. And during my presentation, I'm going to mention the challenges of these technological areas for OEMs. I will start with the history of vehicles and with the weight of vehicles, why it is increased and can it be decreased, the weight of the vehicle. I will be mentioning this history of vehicles. After that, electrical vehicle technologies, connected vehicle, which is very important to decrease the weight of the vehicles. Also, this is the big challenge for the OEMs. I guess maybe we do not know, but we can be out of business. Maybe unmanned aerial vehicles, flying cars with using sensors, and autonomous vehicle traffic management system. Also, it must be set, and battery and innovation energy technologies, sensors and software technologies, how it will be affect our OEMs, and electrification technologies and advanced material technologies are important for sustainability also. At the end, I will come to the conclusion and I will go. Okay, very fundamental history of the vehicles are presented in the slide with the invention of the wheel, and the weight of the vehicles have been increased until 2023. The main cause of the weight increase is new passenger safety regulations in case of accidents. So in order for protect passengers, pedestrians, design of the vehicle have been improved, including seat belts, airbags, and stronger body parts for improving the crash performance. So we can see the increase the weight. To comply with the safety regulation, the vehicles have become heavier. The weight increase of the vehicle are not only the safety regulations, but also additional infotainment devices required by the customer. For the competition case, we had to have some infotainment devices. Could we see the weight of vehicle increasing with the new safety regulations in near future? Usage of autonomous driving technologies using sensors, the weight of vehicle could be decreased. The target must be develop an environment which the vehicle cannot get into an accident with autonomous technologies. So this strategy is going to increase the need for sensor technology to be developed in coming years. So that way we can use more recyclable materials, because when we have the recycled materials, we have some crash performance problems and durability problems. We can use sensors to use more recyclable and sustainable materials on the automobile. And also there are 4 types of drive systems for electrical vehicles. One is fuel cell, and the other one is hybrid electric vehicle, plug-in hybrid vehicle, and fully electric vehicle. We are focusing on fully electrical vehicle because it is more not as complex as conventional vehicles. I tried to summarize what is the reason behind the switching to electrical vehicle. Electrical vehicles are less complicated compared to conventional vehicles. A vehicle with an internal combustion engine has about 30,000 parts. So number of parts 50% less in electrical vehicle. Cost of development also less. Drive cost less compared to conventional vehicles. High operating cost is less. Most countries take less taxes and give more incentives for electrical vehicle for sustainability reasons. And I mentioned also before autonomous driving, autonomous technologies, connected and autonomous shared vehicle technologies are also essential for future automobile industry. Transformative technologies such as connected vehicle technologies pose new challenges and risks as well as their benefits. Cybersecurity is one of them. Communication system, electronic components in the vehicle, infotainment units, and software constitute the channels for cyber attacks. In connected vehicles, it's investigated that primarily the communication with the infrastructure, then communication between vehicles, and finally communication of vehicles with the devices on pedestrian will be developed after 2030. This strategy is going to increase additional safety parts on the vehicle that's going to reduce cost and weight of the vehicle. So it's important the vehicle to see pedestrians, devices, and vehicles each other, so we can take out some of the safety products on the vehicle in order to eliminate the cost and weight of the vehicle. So autonomous vehicle is going to be increased, and it's estimated that 45% of the global new car sales will be at tier 3 or higher in connectivity by 2030. The future challenges of the automotive sector could come from the aviation industry, as I mentioned before, replacing automobiles with the unmanned aerial vehicles and unmanned aerial vehicles capable of vertical landing and takeoff. If it comes before or close to 2030 with this successful experience and testing piloted vehicles, unmanned vertical landing takeoff devices, autonomous OEMs could have some trouble because they don't need to have any infrastructure. They just go on air. And also for autonomous vehicle, we need vehicle traffic management technologies must be ready for the autonomous vehicle, and some regulations must be set also. Another issue is the battery and innovative energy technologies. Lithium-ion battery prices were 1,200 per kilowatt in 2010, dropping from 89% in 2021 to 132 per kilowatt hour. But in 2021, it's going to be less than $100, and coming years, 2030, it will be less than $80. So this is going to make electrical vehicles cheaper. And another thing in electrical vehicle, a battery management system to be used in automotive is usually developed and manufactured by OEMs and suppliers. Due to the transportation difficulties of the battery module and packaging production and quality cost concern, it's seen that manufacturers, companies, they developed also their battery pack inside the factory. And sensors and software technologies are going to be increased 100% by 2030. So our vehicles will be like computers, I would say. We can see here number of lines of software code on the future cars are going to be reach 300 million lines. Mobility device software is seen as the most important transformative innovation after smartphones. That's coming very fast. Also, electrification technologies are going to be increased in the areas power electronics, power electronics components, and a drive. And in the next decade, it's expected that mobility sector will be shaped not only the electrification, connectivity, autonomous and shared transformation, but also within the scope of the circularity and sustainability with the development of material technology. The new circular and sustainable materials development are very crucial for OEM perspective because the new tax regulations are going to be issued according to company's circular and sustainable rate. And as a conclusion, there are three challenges we found out about the automotive industry: selection of right power storage. One country selects a lithium-ion battery. The other one is fuel cell electric vehicle. Other one is, so which one wins? We will see. And the other challenge, as I mentioned, comes from aviation sector, and the new tax regulations are going to be issued according to company's circular and circularity rate. This is also very important for survival issue for the OEMs. Thank you very much. If you have any questions, I can answer.
Thanks a lot, Kemal, for this presentation. I think that's very fascinating that by solving its own challenges, making batteries more powerful, making vehicles more lighter, you also create your very own competition because all those technologies, of course, enable lightweight aerial vehicles much more and make them more feasible. So that was a very fascinating angle there. We'll save the questions for in 10 minutes because before we'll complete the picture with Yavuz Emre Yakci. He's the Research and Development Manager at FarPlus. FarPlus I already mentioned earlier, so he'll now complete the picture from the supply chain perspective because all innovations and developments in the automotive industry only work if supply chain stakeholders and OEMs are working hand in hand. So let's get that picture. Yavuz, are you with us? So, yes, here you are. Perfect. I now can hear you.
Hello, everyone.
We can hear you. You can start sharing your presentation and then you're ready to go. In the meantime, let me remind Jose, if you want to join us in the chat, Jose, we still have those questions. You can feel free to provide some information or links in the chat to the questions earlier for Bernd and Jan. Let's make use of that chat.
Okay, can you hear me?
I can hear you. We can see your presentation. You're good to go. The next 9 to 10 minutes are yours.
Okay, this is Yavuz Emre Yakci. I am the R&D manager of FarPlus. I'm going to give you a quick overview of what category of what type of tier 1 we are, and then I will move on with the sensors. So we are automotive injection molder, a couple of production plants in Turkey and some other geographies, and we supply to many OEMs, and we learn from them, and Tofaş Stellantis is one of them with which we do very valuable R&D projects. And this is an overview of group of companies, not only for automotive, but the group of companies also do productions and technologies for home appliances, mobility, life sciences, and etc. And in the past couple of years, we were lucky to be involved in various EU projects, especially focused on sustainability and digital transformation. And these projects have taught us a lot about how we shape our business and products towards future. So I like this simple drawing of innovation very much. It's not only innovation. I think it's your product portfolio, how you forward your plant. So not only the technology and the customer demands, but in the latest years, we feel the global hypes and crisis also affect us to modify our businesses, our way of productions, and I'm going to mention about sensor topic. What does sensor topic mean to FAR+, and what are the challenges regarding technological improvements, market expectations, and some global hypes and threats. So one of the global hypes is, so we have to modify our productions towards industry 4.0. We have started this journey some years ago. We are collecting data from our main business equipment, injection molding machines, and other sensors in the plant, especially to control the quality. Many sensors are already in injection molding machines. These standard data, I would say, is like around 70 parameters. If you go in detail, it would go up to hundreds. We collect this data in every cycle of production, and we try to understand what parameters affect the quality parameters, in what conditions, sometimes from season to season, from week to week, from weather to weather. The data that we collect from the plant, we learn as much to supply more quality products, and here again, what kind of parameters we get from injection molding with Industry 4.0 solutions and sensors I have mentioned in here. The specific sensors which are not in the injection molding machine can be put in the tools. That can be piezoelectric sensors, strain gauge sensors, and surface mounted thermocouples. In the Revolution project, we have moved a step forward. I'm not going to give too much detail, but since we are in the era of circularity, we should be able to process recycled material as much as possible. Therefore, our production should be flexible as possible, and we should be measuring some specific material data during the production. There should be these kind of measurements should be taken out from polymer labs, plastic labs, and put into shop floor. We are working towards this kind of improvements in the Revolution project. This is also a type of sensor. Know your material, not before, not after the production, but in an inline way. Know about it during the production, and act according to, with the support of AI. Non-destructive testing methods are becoming popular in automotive. When we produce complex parts, we don't want them to be sent to scrap area or have any problems at the customer. Just like in medicine, radiography, acoustic, and ultrasonic testing are made to complex parts. We could see the interior composite structure, whether it's perfectly produced or not. And if not, we can do the necessary modifications during the production. These were about plant and production. Our products are also becoming more sophisticated. We call them value-added parts, and we have been doing this kind of parts. We will use this kind of sensor in plastic part technology also in Revolution. Touch control parts are really popular. We are able to integrate injection molding parts with this kind of sensors. And this slide mentions a little bit of it. And the technology can be on any material. You could, without any buttons, you can use any part in the car to control any function. And also another issue is again, as a part of circularity, we have to monitor the behavior of the parts. So interface measurements about the materials during the parts life cycle is becoming very crucial, and in our project EMAC is doing really good research. This is our near future regarding sensors. We will have sustainable materials integrated to technological applications like wooden surfaces on the right side. Collaborative robots will be working with operators, and automated guided vehicles will be working together, connected to other IoT sensors. And this is our near future as a tier 1, making our progress towards it. And I can say EU projects are really supportive in this goal. And this is all about my presentation.
Thank you, Yavuz, for the presentation. Let me welcome Kemal back on screen, and then we'll just take 2 or 3 minutes for spontaneous questions in that regard. So Kemal, you can turn on your camera and your microphone again and join Yavuz on screen. And if you're listening as participant, please make sure to post your questions in the chat. And Yavuz, I think you have to stop the screen sharing, otherwise... yeah, just perfect. Exactly. So if you have questions, please post them in the chat and I'll forward them to Kemal and Yavuz. Now that's interesting, Yavuz, because you said that depending on the weather, temperature, etc., the quality of the material changes. So now it makes sense with what we heard earlier about the data and AI approach at the Revolution project, because that probably goes hand in hand, if I understand it together, that once you have the data, you can track it, you can develop or use machine learning and AI to tackle that problem. Is that correct?
Yes, exactly.
Nice. What sort of developments did you already have in being part of the project?
We can say that the material manufacturers did their responsibilities really good. The recycled materials have been prepared to be produced in challenging parts, like structural and aesthetical. Like 5 years ago or 10 years ago, recycle was only considered as a cost reduction material for simple parts, but now with the demands of sustainability goals, we need to use them in structural and aesthetical parts, more challenging parts. So this has to be followed by many partners, and we can say the material providers have prepared really good materials in Revolution project. Now it's our time to process them and monitor them during the production and achieve those goals of challenging part.
That's great to hear. Thank you. Kemal, how has it been for you being part of the project? How long did you guys need with all the various stakeholders to agree what challenge you actually tackle? And how much time were you able then to spend on the actual work and research itself?
Well, the bottleneck for us is we have the recycled materials parts, and we put these parts on the vehicle, but we have some tests, durability tests. So mostly we have some problems. I mean, we have 3 parts. Okay, we don't have much problem these parts put on the vehicle. However, to make more parts and lightweight, we have to put also lightweight issue, a lightweight challenge on this vehicle, because we have to decrease our weight, vehicle weight, in order to increase the electrical vehicle range. So we have to have more parts recycled and lightweight and less cost. This is the challenge for us. I mean, we have been working on this continuously. So because it's very a difficult issue, sustainability and circularity management is going to be crucial for automobile industry, because of the taxation regulations according to zero carbon emission will be affect us, because how competitive you are, they will put you some tax on your vehicle, so you won't be able to sell to European countries maybe. So that's very important to have lightweight, less cost, and sustainable products to be produced on your vehicle. So we have been working, but I cannot give you the specific year. How can we increase these parts on the vehicle? But we have so far 3 parts. We have no problem. We have been working as Revolution partners.
You mentioned that, of course, you have to cover several criteria. It has to be cost efficient. Of course, the automotive industry is very cost sensitive and really geared towards efficiency, has been so for decades already. Now, would you say that the big challenge is always either going for cost effectiveness or sustainability and circularity, or is it actually a synergy where if it's lighter, it also becomes cheaper, or if it's circular down the end, you save costs? How balanced is the relationship?
All of them we should have considered. This is the biggest challenge for the OEMs, because if we don't do circularity and sustainability management side, we could have maybe cheaper vehicle, but with the taxes, we are going to lose this competitive advantage.
Thank you. And quick question, was how important is it for you to really have the collaboration with the OEM? I know in Germany, some OEMs are taking the light route. They're just taking their sustainability goals and push them down into the supply chain, into the tier 1 suppliers, and then they have to see how to figure it out. So is a project like this a great opportunity to actually together come up with a solution rather than just having to solve the problem for the original OEM?
We are doing R&D in both ways actually. It's nice to have an OEM aside in the project and focus on the problems together. And sometimes sometimes with internally funded small projects or academic related projects, we try to prepare for the future. We feel what OEM needs. So we also do this kind of project. So I think it's valuable in many ways. So we try to fill all the checks. Yeah.
Thank you, Yamus, and thank you, Kemal. We'll have you back in 20 minutes for the final discussion, but thanks a lot already for giving us this insight. And that means we'll now move on to the research organization side, and we'll see what technical solutions are in store in Revolution and in LEVIS. We'll start with Revolution, and for that, actually, we'll hop across the continent. And I'm very glad to have on board Frederic Bozoit. He's the team leader, Smart Objects for IoT at the IMEC, so the Inter-University Microelectronics Center, basically the largest research center for nano and microelectronics in Europe, based out of Leuven in Belgium. Great to have you on board. Very curious to hear what sort of solutions you have developed in Revolution.
Okay, thank you for the nice introduction. I will share my slides.
Perfect. I can see your slides in full screen. I can hear you. You're ready to go.
Okay, thanks. So, good morning, everyone. Thanks for joining. So I will talk a little bit about our work on sensor integration in plastic parts for automotive in the frame of the Revolution project. So I'm part of CMST, which is called Center for Microsystems Technologies. We're part of IMEC and Ghent University. We're based in Ghent, in Belgium. You can see here a picture of our offices. We're based on the 6th floor. And next to our offices, we have lab facilities. So we have electronics labs, chemistry labs, where we can make prototypes. And then very important is we have clean room facilities where we can do more like microelectronics and integration technologies in a clean environment. So our research group is specializing in packaging and integration technology for electronic and photonic integration systems. So in this way, we can make novel smart microsystem applications. In our group, we are about 66 people from 17 different nationalities. And it's a mix of more academic people, professors, postdoctoral researchers, but also highly skilled research supporting staff. In our group, we're focusing on different R&D domains, like flexible microsystems for healthcare, smart objects for Internet of Things, and also optical microsystems. We have clean room and labs facilities, like I mentioned. Also, some people in our group are giving courses to engineers in the masters and in the bachelors on electronic sensors, microsystems. On average, we have something like 40 scientific papers per year. So far, we also have 2 spin-off companies, Morrow focusing on smart eyewear, and then also Azalea Vision working on smart contact lenses. On the slide, you can quickly see some realizations. So we're working on smart textiles, optical microsystems and sensors, smart contact lenses, so a contact lens with integrated microsystem functionality. We're working on optical interconnections between photo ICs and waveguides. And people are also working on implantable microsystems. So in this presentation, I will give a brief introduction to structural electronics. Then I will tell a little bit about our work about sensor integration in the frame of the Revolution project. And I will then tell you what our future work is in the frame of the Revolution project. So what is structural electronics? Well, it's a technology, a recent technology that is getting a lot of attention in recent years. So it's about nice integration of electronic functionality, sensor functionality in irregular shaped objects, plastic objects, Yeah, what is the rationale of that technology? The aim is to, for example, if you look at this traditional control panel, it has a lot of different parts, a lot of mechanical parts, electronic parts, which are assembled together. And the idea of structural electronics is to reduce the amount of parts, to integrate sensor functionality and electronics directly on plastics, which are thermoformed and then overmolded to create these nice human-machine interfaces. So this is an example of Tactotech. So yeah, by applying this type of technology, you can reduce the weight and the thickness of these devices. So it's very interesting for automotive, and a lot of OEMs are focusing on this type of technology. What are we doing in our group? So we have two technology tracks. So we're doing research on the use of thermoforming to transform a 2D circuit, like you see on the picture on the left, into a 3D circuit. So our approach is to make a flat, stretchable circuit first, which consists of stretchable interconnections using copper, for example, with assembled off-the-shelf SMD type of components. So in this case, you have LEDs, but it could also be sensors. They are embedded in a thermoplastic material like polycarbonate, polypropylene, or PEG, or whatever in function of the application. And then using a thermoforming process by heating it up using a mold, you can deform such a flat circuit into a 3D circuit. And of course, the challenge is to make sure that your electronics survive the thermoforming process. So in our case, the conductivity of the tracks is not changed because we're using copper and these stretchable interconnections. Another challenge is, of course, the positioning of the components to make sure that they end up at the right positions. So these are things we are investigating in our research group, and we also have some recent publications on this. So that's one approach. And then the other thing that we're looking into is to use injection molding to overmold flat and also thermoformed electronic circuits. So we start with foils, thin foils with electronic components on, and then we work together with injection molding partners where we give these type of foils to, and they perform then the overmolding on our foils. And here the challenge is, of course, to make sure that you have a good adhesion between the foils and the plastics, that the electronics survive the overmolding process, so in function of temperature and pressure. And then you can end up, if it's possible, you can end up with integrated functionality into plastic parts. We also have some nice recent publications on this topic. So these are two application examples from previous projects. So this is a smart ankle foot orthosis, which was made using stretchable circuit technology embedded in polypropylene. So the foil was thermoformed in the shape of an orthosis. And in that orthosis, you have movement sensors to track, in fact, the gait of impaired people. And we also have wireless communication, a battery, and local signal processing to wirelessly transfer the information from the movement sensors embedded in the plastic to a mobile app. That's one example using thermoforming technology in plastics, and another one is the integration of LEDs for luminaire type of applications, where we used standard Osram LEDs integrated in this then omnidirectional device. So then we come to the sensor integration in the frame of the Revolution project. So here in Revolution, we want to integrate sensors in the thermoplastic rear crash box, which is one of the demonstrators that we're building. to monitor the structural health of that component throughout its service life. So currently we're making use of piezo-resistive strain gauge sensors to monitor the deformation in the plastic part. And yeah, the idea is to integrate these sensors in a way that we are not changing too much the weight and the volume of the parts, and that we try to minimize the sensor system. And of course, yeah, we want to limit the amount of electronics that are introduced into the plastic parts. So the idea is that the bulk of the sensor system remains outside the plastic, or that it's easy to separate the electronics from the plastic. So this is the concept that we're working on. So the idea is that based on the technologies we have, that we make an electronic foil with the sensors on it. So in this case, strain sensors, which are applied on a foil, and that we have a small amount of electronics that can read out the sensors, and that we can wirelessly transmit that sensor information to an external device which is in close contact with the plastic part. So if we have these foils, then that we overmold the foil, so that we introduce such a sensing foil during the overmolding or the injection molding process of the device. If that would be too challenging, the idea is then to glue it afterwards. So that's also an option. So this is then the overall architecture of our system. So the plastic part with some integrated sensors, and then a wireless readout of the sensor data. So why this choice? Because we do not want to introduce a battery in the system for the powering of the sensors. So here we have wireless energy transfer also to the plastic part. So this is the current realizations. So we're realizing these foils based on polyimide copper foils. Typically, the polyimide is about 50 micron and the copper 35 micron. We started with designs fitting in a dog bone shape to do characterization before going now to the actual crash box. So we have the NFC antenna directly etched in the copper, and then we have also the contact pads for the assembly of the strain gauge sensors. So during the project, we have already done quite some overmolding trials at Varplas, using in the project different thermoplastic polymers. Recycled polymers are used. So these overmolding trials have been performed on our foils to mainly check the adhesion between the sensor foil and the overmolded part, because it's important to have a good adhesion for making sure your sensor is capturing the strains. So here you can see we have a good adhesion, about half to 1 Newton per millimeter on average. It's still possible to separate the two. So also in terms of recycling, we can still remove the foil. And then here you see a quick demonstration of the sensing capabilities. So this is the dog bone with the sensing foil. There are 5 strain gauges on it, but we only measure here 1. And during the bending of the device, we're able to capture the local strain. So it's in ohms, which needs to be translated in the strain. But as you can see, the feasibility has been demonstrated. Okay. So you have, on one hand, you have the foil with the sensors, but in parallel, we're also working on a small hardware board, including a microcontroller for doing the signal processing, including an NFC chip for the wireless transfer of the data, but also for the wireless energy transfer. So the latest design is here, so it's about 2 by 2 centimeter. We have an USB connector. If we want to do a long time monitoring, it's possible with our design. So you can just plug it to a computer and read out the sensors. But during the use then, or during checking the sensor data using NFC, this part can be removed. And the idea is to assemble this PCB then on the foil, on the outside, or also maybe inside the polymer. But this we still need to try. Okay, so what is the future work in the project? So we will, on the short term, perform more trials on dog bone shapes for sensor characterization. Then we will make a dedicated sensor foil compatible with the rear crash box device. We already have some concepts, but I'm not able to show them here. And then we will perform performance trials after summer in September. Okay, thank you for your attention. I hope you enjoyed the overview, and if there would be questions, there will be time after the next presentation to answer them.
Yes, thanks a lot, Frederick. That's awesome. I already have a couple of questions for sure, because that was very interesting. But I'll have to save them for later, because first we, of course, want to have a peek into your sister project, into LEVIS. Thanks a lot, Frederick. See you back in 15 minutes on screen. And welcome, Antoine Latour, Research Engineer and Technical Coordinator at CEA, or CINEA, the French Alternative Energies and Atomic Energy Commission. So basically, the CINEA is focusing on 4 areas. It's defense and security, low carbon energies, technological research for industry, and fundamental research. And as such, of course, is a very interesting stakeholder to have in the LEVIS project. Welcome, Antoine.
Hello, everyone. Can you hear me well?
I can hear you well. See, Antoine. Here we are. Perfect. And
Okay,
in a second, you'll be in full screen mode. So
should
then
be okay now.
Yes, just click on full screen mode so we can see the slides in full screen, Antoine.
It's in full screen mode, actually.
It is?
Yeah, it was.
On the bottom right, you know, the little, if you go down with your exactly. Oh, nothing changes. Okay. Huh.
Is it okay now?
Oh, I don't know how it looks for the other participants. I can still see the your main slide and all the other slides on the side. So it's not in presentation mode yet.
Well, on my screen actually is in full screen.
Oh, interesting.
Let me try something else.
Mm-hmm.
It's weird because I only have one screen here, so.
Mm-hmm. Maybe if you zoom in, it'll solve it. We use it as it is, and just scroll a little bit up.
So, is it better now? You see
It's
full
better,
screen?
but now it's a little bit cut, so you need to scroll a little bit up so we see
weird.
the full slide again. Yes. No worries. I think we'll use it as it is, but you have to scroll a little bit up in the image so that we can see the top part of the picture. Perfect. Just use it as it is. And then you can, of course, put your email address into the chat later and send around the slides for those people who really want to dive into the details. Let's go.
Great. So hello everyone, I'm Antoine Latour, I'm working at CINEA, and I'm going to give you an overview of what we are doing in LEVIS concerning sensors for electric vehicles. So my presentation, actually, this is the outline of the presentation. So first I'm going to give you a very short overview of CINEA LE10. Then I present the printed electronic platform we are using for this project. Some example of sensors for automotive industry, and I go deeply in sensor used for LEVIS application, mainly for structural F monitoring. So concerning CEA, actually, so yeah, it's weird because I have some animation on that one. CEA is our RTO, French RTO. We are based in Grenoble. We are something around 20, more than 20,000 people working. And we have different division. Actually, I'm working in a division where we are working on new energy, but also on structural electronics. So I don't have to explain what is it because we have a nice presentation about structural electronic just before. And to work on this, to develop some sensors using structural electronic techniques. This is more or less the kind of sensor we are developing at CEA. So depending on the type of substrates you are using, we can integrate the sensor in different kind of object. So for instance, if you use a flexible substrate like a PEN or polycarbonate foil, um, you get something which is rather flexible, but you can also print this sensor on different kind of substrate like a TPU, which is very conformable, so it can follow a 3D shape, for instance, but also on some stretchable substrate like silicon, when you need application, when you want to stretch the substrate of the object. So for LEVIS project, we are mainly working on conductive tracks. So we print some conductive lines in order to address some sensor or to make some touch sensor, for instance. We are also using some piezoelectric materials to print some piezoelectric transducers that are going to be used in structural health monitoring techniques. So that's more or less the different type of printed sensor we are developing in LEVIS. So actually, we are using different kind of tools on our printed electronic platforms for LEVIS. So first, we are using some screen printing tools, like the picture you can see here. We also have some pick and place equipment and some laser cutting equipment. So laser cutting make it possible to after printing to cut the parts and get some models so that you can be integrated in the 3D object or plastic part later. And the pick and place equipment, actually, it's mainly to do what we call hybrid electronic. So we are using either printed processes, but also regular surface mounted device glued on the plastic foil. So concerning sensor for automotive application developed at CEA, actually, it's more or less the same process than the one presented just before or presented also by Farplas. Actually, the main difference is that we are using printing processes. So we use a screen printing process in order to print some conductive lines, some piezoelectric transducer, some force sensor, humidity sensor, for instance. And then we can use, as I mentioned before, pick and place device in order to add some functionalities such as LED or microcontroller. Then we can give a 3D shape using a thermoforming process and do the overmolding by injection molding in order to get a plastic part that can be integrated in automotive application. So for instance, here you can see a dashboard, a plastic dashboard with capacitive interfaces and haptic feedback in order to give some feedback to the user when he push the button. Actually, you don't have any button anymore, as I mentioned before. So you have a seamless surface with decorative foil, but also a sensorized foil with some capacitive sensor in this example. Here you can also see a picture of a small dashboard with some LED functionalities and capacitive sensing. So if we go deeper in the LEVIS project, actually there are two different kind of sensors that are going to be used, but all of these sensors are made by printing processes. So here you can see some pictures of our printing equipment. So we are using a sheet-to-sheet equipment. We can print on Gen 1 substrate, so that means 32 by 38 centimeter. So you may know, I think, a screen printing process, but you can design a screen, a mask, with the different shapes, different localization. So it's very customized process. You can use different kind of materials. So if you want some force sensor, you can use piezoresistive materials. And in our case, we are mainly using conductive inks to print some routing conductive paths, but also some electroactive polymers, which is a copolymer based on PVDF developed by Arkema Piezotech to print the piezoelectric transducer you use in the SHM application. So this is some examples actually of piezoelectric transducers used for SHM for two demo case developed in LEVIS. So we are developing some SHM approach for the control arm application, but also for the battery case demo case. In that case, we can use different kind of substrates, but we focus on two different substrates, the polyamide, but also the TPU, in order to study their performances in the SHM application. We print polymer electrodes, which are made up by P.PSS, which are very thin electrodes. And non-metallic electrodes. We use, as mentioned before, an electroactive polymer, which is made of PVDF TIFE, which is a copolymer. And in order to increase the sensitivity or the performance of the actuator, we can stack different piezoelectric on top of each other by printing them on top of each other in order to increase the sensitivity of these sensors. So the typical stack thickness when we stack the actuator together is between 10 and 50 micrometers without the substrate. So you can see here some examples of the architecture we are using. So it's a capacitive architecture with electrodes and in between the electrodes ferroelectric materials. So you can see we are designing some screens in order to print both conductive lines, but also polymer electrode and electroactive materials. So you can see here some example. After cutting the parts, you can have some piezoelectric elements printed on plastic foil, then being integrated in a composite compositive material using some composite processes developed in LEVIS project. We are working on another kind of application actually, which is monitoring a bus bar. Actually, a bus bar is the metallic part that is making the contact between different cells of the modules of the battery, creating some parallel or series connection. So the goal of this demo case is to get the bus bar smarter by adding some functionality. So we are working on two kinds of sensor, let's say. So we print conductive lines on the insulating film, and on some part of the conductive lines that are open, and we have a contact between the conductive lines and what we call the voltage probe actually. So we have a contact between this probe and the metallic part to get some voltage measurement, but we are also able to mount some temperature sensor on different localization of a bus bar in order to get let's say a rather good mapping, thermal mapping of a bus bar to monitor some heat propagation on some strange behavior of the cells during the working of the cell. Actually, so you can see some examples. So we have a large equipment, so we can print on larger substrates, something like 50 by 30 centimeter. So you can see here conductive lines plus an insulating layer on top of that that are going to be processed during the bus bar fabrication. So if we go a bit deeper in the results obtained in LEVIS concerning the structural health monitoring, so actually you may know what is SHM, so structural health monitoring. So it involves the observation of and the analysis of a system over time using periodical sample response measurement in order to monitor different changes of the materials of the structure of a system. So the objective of this approach in LEVIS and in SHM in general is to detect and predict some damage in a component. So in LEVIS, actually, we are mainly focusing on one of the steps of the SHM, which is the experimental implementation. So we are testing some piezoelectric samples and developing some algorithm. So we are mainly working on two types of techniques. So the first one is acoustic emission. Actually, we use the piezoelectric element as a sensor. So we are listening to some signal that are but the signature of which can be associated to some defect like an impact, some delamination, some crack into the system. So it's just passive and listening system. The other technique is the ultrasonic guided wave monitoring. In that case, actually, we are using transducer as sensors and emitters. So we emit a signal in the hundreds of kilohertz range, and we receive the signal with some other transducers, and we can compare the signature between the signal acquired with a baseline state. So we can monitor quite the same type of events like cracks, delamination, debonding, and even corrosion. So in LEVIS, we focus first on the acoustic emission. Actually, we are using this technique to monitor some delamination in this project, and mainly in the control arm application. So as I mentioned before, we use this piezo transducer, this printed piezo transducer, as a receptor to detect the signal. So we are running a study in order to study the sensibility of different architecture or sensor developed at CINEA to choose the most suitable one in terms of substrate. I mentioned that we can use different kind of substrates, but also number of stack layer, and also the size of the shape of the sensor. So we are making some comparison between sensor embedding during the manufacturing process, so under the resin, but also a sensor just bonded on the surface. So you can see here a picture of some sensor embedded on the composite foil, and we are conducting the sensitivity analysis with that. For the other technique, the ultrasonic guided wave, actually, this technique is more suitable to monitor debonding between two dissimilar materials. So in LEVIS, we are using this technique on the battery case application. So we want to check the debonding in the internal beam between composite fiber and aluminum profiles. So in that case, we are using some PZT piezo transducer, and one of them is used as the emitter. The 3 over 1 in the test vehicle we are using, the 3 over 1 are used as a receiver. So we perform some DCB tests with some dummies, with some test vehicles between carbon fiber and aluminum samples, and we collect some data in order to feed some algorithm. In the meantime, we also conducted some finite element simulation of the propagation of the waves in these dissimilar materials with different kind of adhesive joints. We study the impact of the length, the debonding distance. So we are running this application right now, and we can find some correlation between the damage size and the signal received. So I think that's more or less all for my presentation concerning LEVIS. So I'd like to thank all the CA team, the CINEA team, because it was a joint presentation between CINEA and CA, and also, and of course, the European Commission and the LEVIS consortium. So I don't know if you have any question, and I apologize if the presentation was not, I was not able to do it in full mode presentation.
Thanks a lot, Antoine. Yes, Frederick, do you want to rejoin us on screen just for a brief Q&A, and then we'll go into the larger discussion afterwards. Now, again, to me as an outsider, it looks like actually not only projects in themselves are interesting, but it could actually be interesting for you guys to talk to each other from project to project. Is that communication happening as well, Antoine and Frederick?
Not really until today, but
Not yet.
It will happen in the next future. Actually, we are working on quite the same topic with the same techniques. So I think, yes, it's something we should implement in the next few days, few weeks.
I mean, I know to me it looks very similar. For you, you know that what you do is worlds apart, but still there seem to be some obvious synergies. Frederick, what I wanted to ask you is that you explained the whole the reasoning and what you're doing. Is it a particular challenge for you to mold these sensors into 3D structures, working with the PCR, so post-consumer recyclate? How much of a, like, how much is there, because that is what the project also is covering as such. You didn't get into detail there, but is it like challenging to use these materials or to have a steady flow of the same quality PCR, et cetera, et cetera?
Well, like I explained in the presentation, we are making the foils and then we provide them to the partners doing the overmolding experiments using the recycled polymers. And so far, the overmolding trials went quite well. We do not really see a difference between virgin plastics or recycled plastics. Also in terms of adhesion between these recycled plastics and our foils. So far, this is running well. And then our idea is also then later on to split the electronics from the plastics again. And you've seen we have sufficient adhesion for the sensors to do the readings, but it's still possible to separate the two from each other. That's also our approach, that the sensing foil is on the outside of the plastic, so that it can still be removed.
Yeah. Do you know what sort of PCR would be used in the future? Is it PET plastic? Is it literally like a post-consumer household plastic, or is it post-consumer plastic from within the automotive industry?
Well, within Revolution, there are some partners, specialized in collecting, these post industrial plastics. So I think the scope within the Revolution is really using post industrial plastics, which are collected from everywhere, recycled, and then used to make these new automotive parts. So that's currently the main scope.
Now, Antoine, last question before we also open up for the larger discussion. I mean, both your organizations, I guess it's your daily business to cooperate with other institutions, with other stakeholders. So to what extent is then LEVIS or Revolution a special project for you? Or what has it enabled your organization in regards to all the other projects you're probably running?
Well, for our case, actually, it's true that we are working on sensor development, printed sensor development, but for different kind of application. And what is new in LEVIS for us actually is the use of this piezo transducer for SHM application. Actually, before we use them in automotive application, but as San mentioned, we can use this piezoelectric element as a pressure sensor, actuators actually for human-machine interface, so what we call haptic, so they can create some vibration. Once you have embedded this piezoelectric element in a plastic foil, a decorative plastic foil in a dashboard, for instance, you get a touch sensing functionalities. You have feedback. And this is what the topic we were working on before. So what is new in LEVIS is to use this piezoelectric performance for ultrasonic application, so structural health monitoring. So that's the topic which is new for us, and that's why we are very glad to work with Itainova, which has very strong competencies in structural health monitoring.
Frederick, before you start your answer, I'll just also invite Yuvas, Yavuz, and Kemal back on screen. And while they take their time to switch on the screen and the microphone, you can give your perspective, Frederick. So if you compare it to other research projects you're involved in with your organization, how does Revolution differentiate itself?
Well, it's a bit similar. So far, all the projects we had was on all the projects we had so far on structural electronics was to integrate Yeah, it was also more related to human-machine interfaces, so to have LEDs and touch capabilities and plastic parts. So for us, what is new is the integration of sensors for doing structural health monitoring and these plastic parts. So before Revolution, we didn't had experience with it. So now we're learning a lot with this project on this field. We have a nice technology platform to integrate all types of sensors and electronics. And we developed that for different types of applications, like for wearables, for luminaires, for lighting. But for us now, it's the first time to do it. And also, automotive is very challenging in terms of reliability. So yeah, that's also something that we will still face towards the end of the project, to see if we do temperature cycling or humidity cycling of the plastic parts, what will happen with the electronics and the sensing functionality.
Thanks a lot, Frederick. Yavuz, Kemal, do you want to join us back on screen? I'll give you a second. Did we lose Yavuz? Is he still on the call? I only can see you, Kemal. Anyways, we're entering the last round of discussion, so we'll take the last remaining 12 minutes to answer all the questions there are in the chat. If you do have questions for Antoine, Frederick, or Kemal, please post them in the chat. I'll forward them as we have the discussion here. Kemal, let's start with you. Anything exciting already you took out of that project where you know that, well, we are a big step ahead and it's really helping us on some of the challenges we have? So what have you gained from the project already while it's still running?
Well, I think we have learned a lot about the recycle process, because we have 3 parts, and these parts are made from recycled parts, and we put these parts on the vehicle, and we have very difficult tests on the vehicle, because we have to have those tests in order to sell the products to the customers. We don't want the products have some problems on the customers. So before we have to have these tests. So we have quite experience on the recycled materials, how we develop and what parts, what kind of materials we should get. I mean, coming years, probably we are going to have using recycled materials more. We have to use because of the sustainability and circularity management issues. For zero carbon rate, we have to decrease the company's zero carbon rate also. So this project, both of the projects, is going to help us for future development activities for sustainability and circularity management concept.
Just as a quick follow-up question, Kema, you already outlined some of the challenges for the automotive industry as such. What would you say is the most critical challenge? Is it more regulatory frameworks, as you said, taxing of the carbon footprint, for example? Is it more like the cooperation with enough research organization across borders, or the development? What's the #1 priority for you?
The critical challenges for the automotive industry, I would say, bottleneck for electrical vehicle are battery prices and security of the charging stations, and also range of the vehicles. I would say we cannot solve the range only battery technology. I mean, we have to decrease the weight of the vehicle. I mean, if we have a heavy car, and also aerodynamic drag also is important. So the second one is the rapid entry of the electrical vehicle into the market with the decrease of battery costs. Advances in the electrical energy storage and rapid development of autonomous vehicle technology may be threat to existing OEMs, which they are not ready for these technologies. So for these kind of projects, LEVIS and Revolution projects have been helping us to get ready for these coming technologies.
Thank you. Kemal, I think you're sort of halfway in the project, still some things to be developed generally. Where do you want to be once the project has been finished? And do you think there'll be an ongoing collaboration even though the project itself is stopping?
Well,
oh, sorry,
yes.
Kemal, that was
Yes.
my mistake. I wanted to ask Yavuz.
Okay.
Sorry, I wanted to pass the ball to Yavuz since we have
Okay.
him back on screen. My bad.
Okay, sorry. Yes, we want to supply as much as sustainable parts as possible in our portfolio, convert our plant to a more sustainable production plant, and we would like to have parts with their own passports, what kind of energy, green energy they use, what kind of sustainable material they use for the moment. So this is the feature that we believe in.
That's quite interesting that you bring up this this topic, because the digital product passport, of course, is something that in the EU will be happening. That's specifically interesting for the whole automotive supply chain. Do you think that data from the integrated sensors could also in the future, sort of like to update the current state of the parts, and also to see at the in a second life use case or for recycling, to see really how the properties have changed?
Yes, I think so. It's a nice place to store the background and the life of the part. So yes.
Is that something you also have in mind, Frederick or Antoine, when you think about taking data out of the sorry, I think that was more the topics you were talking about, Antoine, gathering data out of the sensors while being in use in the car?
Yeah, you mentioned. Yeah, actually, we are gathering data from the sensor integrated in the car. But could you precise your question? Sorry.
I was asking, it sounded like obviously one purpose of gathering the data of a strain sensor, for example, is to see if the part is still functional. But since Yavuz also mentioned the digital product pass, is it something that you think this data could be used for as well, to document the part properties on the long run, or for recycling or other use cases on the long run?
Sure. Maybe, yeah. For instance, for the battery module or battery case, one of the objective will be to do some periodic inspection and to check if we have any change compared to baseline. But in case of a crash or something, you can also check if the structure has been damaged, even if when doing a basic observation, you cannot see anything, but using this kind of approach, you can maybe reuse the battery box and extend the life during a few years instead of just replacing it. Another topic maybe for instance, for a composite part, like for instance, the control arm is mainly done by a metallic part, but replacing metallic part with a composite one is something maybe tier automotive OEM are not very prone to use because of the novelty of a composite part. But adding some structural health monitoring functionalities, maybe that is going to help OEM to encourage them to use this new composite part, because they have this auto diagnostic functionalities. So maybe it's a step in order to increase the lifetime, but also to decrease the weight of the part of the whole car.
Mm-hmm. And just to turn things around, I know that Frederick talked about 3D shaped objects. Is that something you also look into, Antoine?
Yes, yes. For actually, there are different way of getting a 3D object. One of them, the first one that comes to mind is to print of a 3D object. So to get a kind of maybe a spray nozzle or something that is going to follow the shape and be able to print. But the other option that we are using is to print on the 2D foil and then break into a 3D shape. So there's different option. One of them is to do some thermoforming. So you apply the foil on the mold with heat, and then you get a 3D shape. Another one, if you cannot or don't want to use this one, is to print on a conformable or stretchable substrate. So you print on 2D foil, and then you stretch it and you wrap around, for instance, for wearable application, but you can imagine in car for some interior product. Maybe you can give a 3D shape, not by thermoforming, but by just extending, stretching a bit, like TPU, for instance, polyurethane, which is a bit conformable. You can follow a 3D shape. So for that, you need to print some inks that are compatible with extension, so that are not going to break when you stretch them. So that's one of the topic we are working on in every RTO, I guess, is to find this kind of conductive ink or the kind of inks that can be stretched in the final application.
Now, these projects, obviously, you come together, you have a certain agenda. If you join Revolution or if you join LEVIS, you agree on the challenges you want to solve, but then you start researching, and a lot of times you just by accident come up with new ideas, with new use cases. So Frederick, to what extent has maybe the overall objective changed already since the project is running? Have you come up with novel ideas you did not have in mind before you started? Do you see some additional use cases or outcomes?
I must say that in our case, the scope is still the same and the challenges are still the same. So it's not that we fully that we changed what we wanted to do in this project, but seminars like this today and discussions with partners and other research organizations working on similar topics, that gives a lot of ideas for new topics or new applications where these type of technologies could be applied to. So it's by talking to a lot of people and to the industry that you really learn to know what are currently the challenges and the missing research, and that helps me to define new projects.
You just, I think earlier you talked a lot about integrating, for example, LEDs into the objects, etc. What are maybe the most interesting use cases you didn't have the time to mention? What sort of sensors could you integrate also, apart from the ones you highlighted?
Yeah, well, recently we have the technology, and recently we had some discussions with luminaire companies in Belgium to first of all present the technology and to ask them, what do you see as potential applications or advantages of the technology. The fact that you can personalize the shape or the form factor at the end of the product, that's a nice thing. That you make everything, that you foresee an LED sheet in a flat way, and that later on, depending on the luminaire design, it can be shaped. Typically within luminaires, classic PCBs, so classic printed circuit boards, are used, which are flat. So that limits the radiation pattern of the LED and the luminaire. So this technology makes it possible, starting from flat substrates, to deform it into 3D emitting light surfaces, which is not possible with classic technologies. And then, of course, you could add sensors like touch or gesture recognition, for example, by making some moves with your hands to dim your lights or to whatever needs to happen with the light, that becomes possible in the by using a smart light bulb.
Thank you, Frederick. Now, with regards to time, I'll start wrapping up things. So maybe as a last statement, Yavuz, Kemal, Yavuz, you already showed a picture earlier where we showed like how the research is coming now into the workshop, into the factory floor. You saw like the trend, we could see the picture and the transformation from prototype to application. Apart from what we saw to do it today and what you've been working on as part of the project, what other breakthrough technologies do you see happening for the automotive industry and specifically in relevance to the supply chain?
The industry is transforming. Anything, either production or parts or materials has to change towards alternative fuels, hydrogen and electric, or still for more couple of years hybrid, and the plants has to obey the carbon emission targets. The plants have to transform, and autonomous will be there, or semi-autonomous. The passenger will spend more free time in the car, so they will want more access to infotainment or other controls. So this means more sensor applications on various parts, even apart from the dashboard itself. So all together in the most sustainable way possible.
Thank you,
think
Yavuz.
these are the trends coming here.
That's something we saw earlier also in the presentation. I think actually that was I forgot now, but we saw it earlier. We talked a lot about automotive, but that of course means if you don't have to focus on driving, you have a much more time to look at the sensors, at the surfaces in the car. The more important it is that they're designed in a pleasing and interesting way. Well, that's it. I think we'll be wrapping up here. Yeah, it came out. Just one last sentence. That project is still running. If there is a continuation, which stakeholder do you want to have on board for a future collaboration? Who has been missing so far? One quick statement.
Well, this project, I mean, the benefit of this kind of projects, we have many partners we worked. So after 3 or 4 years, we can have these partners for the development of new project. We can work together, because these research projects becomes like a shelf project, or some of them, some of the information and the development activities just we put on the vehicle and we can sell to the customer directly. But some of them, it has to be waited some years to serve the customer. But of course, we can work our partners for also for production coming years. I mean, these kind of projects also not only development activities of the products, but also we can always realize new Horizon Europe and research projects together for related concept for future development.
Thank you, Kemal. Thank you, Yavuz. Thank you, Frederick and Antoine, for joining us today. If you want to connect with all 4 of them, I think I found you on LinkedIn. So reach out to them. Make sure you use the connections to continue the discussion, and maybe also find synergies between the sister projects. Thanks a lot for joining us today. As you can see in the chat, Antoine already put his email there if you want to reach out to Antoine. Andrea just posted the link to the Revolution project, so you can find all the information for the upcoming webinars. And of course, check in with greenvehicles-levis.eu to stay up to date. Thanks a lot for everyone. Have a lovely afternoon or lunch, depending which time zone you dialed in from.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.
everyone.
Thank you.
Bye-bye.
Have a good day. Bye bye.